Performance problems don't always come from how much memory you allocate. Sometimes they come from how much of that memory is still alive when the runtime needs more space again. Let's dive into this. I'm K1, welcome to my channel. In the third video of this series, we looked at why objects stay alive. In the fourth video, we looked at what makes the GC run. This video is where those two ideas meet. New allocations keep coming in, but older memory is still alive. That's when memory pressure starts turning into performance pressure. Let's use something that looks completely normal. An API endpoint loads a fairly large order object graph. That includes things like the customer, address, payment info, and the order lines. Then the service makes an async call to check fraud risk. As you see, I'm using task.delay with 100 milliseconds just to simulate network latency. From a business point of view, this looks totally ordinary, but from the runtime's point of view, something important happened. The method loads the order, heats a wait, and then still needs the order afterward. So while this request is waiting on I/O, that object graph may stay alive. And if order stays alive, everything reachable from it can stay alive too. The customer, the address, the payment info, the order lines, and all the referenced strings inside the graph. That is not necessarily a memory leak. The memory is still legitimately reachable, but it is being retained longer than the code might make obvious. Now compare that with this version. Same endpoint shape, same business goal, but the lifetime shape is different. Here, the code computes what it needs before the await. So after that point, the full graph may no longer need to stay alive across the async await. That doesn't mean the runtime collects it immediately. It just means this request is no longer forced to keep the whole graph alive while it waits. Same API, but different lifetime. This is the part that really matters. One request retaining one object graph is usually not the problem. The problem is when many requests do it at the same time. If hundreds or thousands of concurrent requests all keep similar graph alive across the same async wait, the runtime is no longer dealing with one longer lifetime. It is dealing with a much larger live set at the exact moment new allocations keep arriving. That is where the pressure starts to build. Now let's put both versions on the load. To make the difference easier to see, I constrained memory to about 1 GB, used server GC, and heaped both endpoints with the same load while watching dotted counters inside Visual Studio. Let me make it clear, this is not meant to be a benchmark for which endpoint is faster in isolation. What I care about is something more specific. What happens when object survival starts affecting performance under load? So I run the app in release mode, do a short warm-up, and then hit the baseline endpoint with 1000 concurrent requests for 20 seconds. After that, I restart the process and do the same thing for the retained endpoint. Before comparing the results, here is what I care about. I'm grouping the metrics into 3 buckets: memory size, lifetime and promotion, and the final performance outcome. The exact numbers will move around a bit from run to run, so don't focus too much on those numbers. What matters here is the pattern. First, memory size. Here I'm looking at the GC heap size, working set, and committed memory. And in the retained version, all 3 moves in the same direction. The heap is much larger. The working set is much larger from the OS point of view, and committed memory is much higher too. So this is not just a small GC detail, The runtime is carrying much larger live set and it needs more memory to keep that live set around on the load. Next, lifetime and promotion. Here I care most about generation number 1 and generation number 2. And this is where the retention story becomes very clear. In the retained version, generation number 1 grows dramatically. That tells us these objects are not dying young. They survive early collections, they get promoted, and pressure starts building earlier. The generation number 2 grows much larger as well. So the problem is not just that old generation eventually gets bigger, it is the whole promotion pattern changes. More objects survive, more objects get pushed forward, and the runtime ends up carrying more long-lived memory than before. Now, one metric can look a little bit confusing at first. The baseline actually allocates more memory per second, but that doesn't mean the retained version is healthier. Allocation rate is measured per second, not per request. The retained version is simply doing less work each second. Throughput drops, the app completes fewer requests, and because it is processing less work, the measured allocation rate also goes down. So in this case, lower allocation rate is not a good sign. It is actually a sign that the application is slowing down. Collection counts can also be misleading if you look at them too quickly. In the baseline version, Gen 0 and Gen 1 collections may happen more often. At first glance, that might sound worse, but here it often points into the opposition direction. It means more of those allocations are still behaving like short-lived allocations. They become unnecessary sooner. So the GC can clean them up earlier. In the retained version, more objects survive those earlier collections, get promoted, and push pressure into older generation instead. So fewer younger generation collections does not automatically means lower GC pressure. Sometimes it means the runtime is carrying more lived memory forward and paying the price later in older generations where collections are usually more expensive. And that brings us to the final bucket, the actual outcome, latency and throughput. In the retained version, latency is higher and throughput is lower. So at this point, this is no longer just a memory story. It has become a performance story. That one lifetime difference, meaning keeping the object graph alive across the async wait, changes the whole memory shape. You get a larger live set, more promotions into older generations, more memory held by the process, higher latency, and lower throughput. That's the connection. This kind of lifetime issue does not always become a visible problem immediately. If the process has enough headroom, both versions may look for a while fine. That's why these issues often stay hidden during deployment and only become obvious later, when concurrency rises, when memory budgets get tighter, or when both happen at the same time. So the right mental model is not retention is always disastrous. The better mental model is this: allocation creates memory pressure, but survival determines how expensive that pressure becomes. Once memory lifetime starts affecting performance, it also starts affecting infrastructure cost. Because the more memory your service keeps alive on the load, the more resources it needs just to stay stable. That's what we'll discuss in the next video. How small C# memory decisions increase your cloud bill. Stay with me and grow with me. See you in the next video.